SwayamPrabha. Digital India. Educated India.
Hello, let us start with our second lecture. Here we are going to continue our discussions on the commonly used coordinate systems and look at some problems. In the last lecture I had started with the Cartesian coordinates, and in this lecture I am going to discuss about the tangent normal, which are tangent normal coordinates, which are also known as the path coordinates, and the plane polar coordinates. Now, tangent normal coordinates are that the name itself suggests that there must be something like a tangent vector and a normal vector. Suppose there is a path as I have shown here, and a particle q is travelling on this path, and this path is in a plane. Now, I can define the center of curvature of this path at any point. Now, how do I define center of curvature? You know that three infinitesimally separated points I can consider on this path, and 3 points uniquely define a circle, and the center of the circle defines the center of curvature of the path at that point where I have taken these 3 infinitesimally separated points. So, suppose I have done that and I have found out the center of curvature at that point where the particle currently is. That red plus symbol that signifies the center of curvature. So, it is the center of the circle that matches with 3 infinitesimally separated points around this location of the particle. Therefore, this C point is the center of curvature and rho is the radius of curvature. Let the instantaneous speed of the particle, which is the magnitude of the velocity vector, so the speed of the particle be v. So, it is magnitude of that velocity vector that is shown. Velocity vector is always tangent to the path as shown here, and the magnitude is v. Then you can imagine that this line CQ, Q is the particle. So, C to Q, the center to the particle, that line is a radial line, and that must be rotating as the particle moves, that must be rotating for at least for infinitesimal motions, that line is rotating, and that I can represent the rate of rotation at that instant of time I can represent as beta dot. I have shown that beta dot on that figure, and that beta dot is the speed divided by the radius of curvature. So, that is the rate of change of that angle that the line makes. Okay, with that definition, now let us come to this figure. Now, here I have started defining my coordinate system. The first thing to note is this vector ET cap. It is a unit vector, of course, it is a unit vector and directed tangent to the path. Therefore, it is along the velocity vector direction. So, ET is a unit vector directed along the velocity vector direction and tangent to the path. En is normal to the path. Now, you can choose 2 normals, one is away from C and one other towards C. Here I am choosing towards C. In tangent normal coordinates we always choose En towards C. Now, you will realize as the particle moves, these vectors Et and En will change. So, they will rotate, they will change directions, so they will rotate. Their magnitudes will remain the same, they are unit vectors, so they will remain unit vectors. Now, velocity vector, the velocity vector in this coordinate system defined by Et and En is simply written as the speed, the magnitude of the velocity vector, speed times the unit vector along the velocity direction. So, therefore, velocity vector is v times E t cap. How do you find out acceleration? Acceleration, you differentiate the velocity vector. Now, as I have mentioned that E t is changing as the particle moves. Therefore, when I differentiate the velocity vector, not only do I generate the time rate of change of the speed, but I also generate the time rate of change of this tangent vector, unit tangent vector E t. So, E t dot. So, this I had avoided in my Cartesian coordinates by fixing it with respect to distant stars, but here I cannot avoid. So, I must find out at what rate E t is changing. So, let us do that. So, E t dot can be defined simply as limit as delta t tends to 0, E t at t plus delta t minus E t at time t divided by delta t. Now, how do I do that? Here I have shown first, let us look at this figure. So, this is E t at t plus delta t and this E t is at time t. I bring them together and I compare these, both of them remember are unit vectors. So, the magnitude will not change, but the direction has changed. How much has the direction changed? It has changed by delta beta. This is the small change of angle of that radial line. The same thing happens here. So, this is delta beta. This is a small change in angle of that radial line. So, small change in the tangent vector also. Okay, so this is a small rotation of that vector, and this is delta E t, the small change in E t vector because of the change in direction. And if you notice carefully, this is in the direction of E n. This is in the direction of E n. Therefore, I can write this small change in E t vector delta E t cap as angle times the magnitude and the direction is E n cap. Now, magnitude of E t vector E t cap is 1 of course, and delta beta. So, therefore, it is delta beta times E n cap. Therefore, the numerator of this, so this numerator is nothing but delta beta times E n cap, and in the denominator sits delta t. Therefore, limit delta t tends to 0 delta beta by delta t E n. So, that is E t dot, and finally, in the limit delta t goes to 0, this becomes beta dot, and remember beta dot was v over rho, the speed over the radius of curvature. Therefore, E t dot is nothing but E t dot is nothing but beta dot times E n cap, and that is equal to v by rho E n cap. Okay, if this part is clear, then we can proceed. Therefore, just I substitute it here, and what I have is the expression of acceleration. So, I can have various expressions. Here I have written in terms of beta dot, here I have eliminated beta dot as v over rho, and I get this expression. Now, this expression of acceleration is very useful in finding out the radius of curvature of a particle, of a moving particle, and that is what we are going to look at next. Okay, these accelerations have some names. This the first term of this acceleration is the tangential acceleration. And how do you find out tangential acceleration? You dot product the acceleration vector with, so as shown here, you dot product the acceleration vector with the unit tangential vector E t cap. If you dot product the acceleration vector with E t cap, you get v dot, and if you take dot product with E n cap, you get the normal acceleration. So, normal to the path. So, tangential to the path and normal to the path, acceleration tangential to the path and acceleration normal to the path we can find out from here, and we can also find out the radius of curvature. So, that is what we are going to look at next. So, this is an example. The slotted links move according to this expression of x and t, where x and y are in millimeter. So, I have two expressions, one is of the vertical slot moving horizontally. So, its x location is given by 16 minus 12t plus 4t square, and there is a vertical slot which is moving vertically, a horizontal slot moving vertically. So, vertical slot is moving horizontally and the horizontal slot is moving vertically, and the motion of these slots are specified by x and x and y as functions of time, where x and y are in millimeter and time t is in second. At the instant when t is equal to 2 seconds, determine the radius of curvature rho of the path of the constrained pin. So, at the intersection of these two slots you can see there is a red pin sitting. I have to, so as you can imagine, this pin will be moving on some path. We have to find out the radius of curvature of the path. Now, here we will use the Cartesian coordinates x, y I have shown here in the figure. I have written out the data which is specified in the problem, the motion of the vertical slot given by x and motion of the horizontal slot given by y as functions of time. Now, it is straightforward to see that the velocity, you can find out velocity by just differentiating. So, velocity of the pin, this is the velocity of the pin. So, velocity of the pin is given by its coordinates. So, I take x I cap plus y j cap. So, the position vector of the pin is x I cap plus y j cap, and I just differentiate this position vector to get the velocity vector, which you can easily find from here by differentiating x and y, they are given explicitly as functions of time. So, I can differentiate to find out velocity vector and acceleration vector. This is of the pin, velocity vector of the pin and acceleration vector of the pin. Therefore, at time t equal to 2 seconds, I can just plug in 2, the value 2 second in time in the expression of velocity vector and find out the velocity vector, which is 4 I cap plus 3 j cap millimeter per second. Now, this is the direction of E t, remember. So, E t is along this velocity direction, but it is unit vector. So, we have to find out this unit vector. So, we switch to the tangent normal coordinates. We define E t as the velocity vector divided by the speed, and that gives us this unit vector 4 by 5 I cap plus 3 by 5 j cap. Unit vectors do not have dimensions. Okay. So, this is E t cap. Then I find out E n cap as a vector which is normal to E t cap. Now, I really do not know in which direction the center of curvature of the path lies, I do not know. So, what I am going to I am going to just consider. So, for example, the path could be this could be the path. So, in that case the center of curvature lies here, but right now I do not know. I will just assume in a certain direction my E n vector, the only thing that it must satisfy is E n dot E t must be 0, and you can see that it does. Now, we have just now derived the expression of acceleration in terms of the tangent normal coordinates. It is v dot E t plus v square by rho E n. Now, why I am choosing this particular expression? Because I have to find out the radius of curvature. Now, this is the expression of acceleration as determined from the tangent normal system, and this I will equate to my acceleration. because this is an absolute acceleration. This is the absolute acceleration of the pin. This is the acceleration of the pin. It is represented in the tangent normal coordinates by this expression, and its actual expression is this. Therefore, I have to now find out rho from here. Now, what do? I dot product both sides of this acceleration with En cap. So, if I dot product the left hand side, I get v square by rho. I dot product the left hand side of this acceleration expression, I get v square by rho. On the right hand side, En, I know the representation of En. So, this is the representation of En. On the right hand side, I use that representation of En and I take the dot product, and that gives me 48 by 5 millimeters per second square. And from here then, because v square is known, v square is nothing but the magnitude square of the velocity vector. So, that gives me rho as 125 by 48 millimeter. So, this is how we can use the tangent normal system, coordinate system, to find out radius of curvature of the path of the particle. Next, we move on to the plane polar coordinates. So, imagine a path as shown in this by this magenta curve, and on that a particle q is travelling. We first arbitrarily determine a point called the pole P, and denoted by this red cross, red plus sign. So, that is an arbitrary point chosen by me. I'll choose it arbitrarily and call that as my pole. I will also choose a direction, a line which I will call the datum line, from where I will measure all angles, the angle to the particle. So, from the datum line I measure angle, and which angle? Angle between the datum line and the line joining the pole and the particle, that is theta. And I also define this vector, the position vector, as r, which is the magnitude times the direction. Now, direction, how do I fix up the directions? This Er is a unit vector along this radial direction from the pole to the particle, and Er, you notice, moves is directed towards increasing r, increasing radial distance from the pole. So, Er is in the direction of increasing r. I also define theta, E theta cap, which is in the direction of increasing theta. Now, these are some important points to note. So, Er is in the direction of increasing r, and E theta is in the direction of increasing theta. So, Er is away from the pole and E theta is in the increasing theta direction. Now, the position vector, as I have already told you, measured from the pole to the particle, is this r vector, which is the radial distance times the unit vector along the radial in the radial direction. So, r times Er cap. So, position vector is fixed. Now, we come to velocity vector. Velocity is found by differentiating with respect to time the position vector. Now, once again you will note that as the particle moves, the Er vector is changing direction, E theta vector is changing direction. Therefore, when I differentiate with respect to time, the frame vectors Er cap and E theta cap, they also will get differentiated, as I have shown you. Now, how to find out Er dot? Again, we do the same thing as we did for the tangent normal coordinates. Er at t plus delta t minus Er at t divided by delta t, limit delta t tends to 0. So, we look at Er cap vector at 2 time instants, compare them, remember they are unit vectors. So, magnitude will not change, only the direction changes. And how much will the direction change? Exactly delta theta that I have shown here. So, that is the change in direction of Er cap vector as it moves from time t to t plus delta t. Therefore, this difference vector, the difference vector delta theta, it has a magnitude of delta theta times magnitude of ER cap, which is 1. So, its magnitude is delta theta, and the direction, if you note carefully, is along E theta. In the limit delta theta goes to 0, it is along E theta. Therefore, this difference vector is nothing but delta theta times E theta, and that is what we are going to use here. So, it is magnitude of ER times delta theta times E theta cap by delta t. Magnitude of ER is 1, therefore, we finally get theta dot into E theta. So, ER dot is theta dot multiplied by E theta. So, theta dot E theta. Therefore, the velocity vector finally becomes r dot ER plus r theta dot E theta. That is the expression of velocity vector. Again, velocity vector, so finally we have been able to represent the velocity vector in terms of the unit frame vectors. So, position vector, velocity vector expressions have been found. Now, we go to acceleration vector. By differentiating the velocity vector, we have already found out. So, when we differentiate the velocity vector, we have time derivative of r dot, which is r double dot ER plus r dot times the frame vector dot. Then here there are 3 terms, because r first gets differentiated, then theta dot gets differentiated, and finally the frame gets differentiated. So, we have this as the complete expression of acceleration, of which we already know what is ER dot. So, this we know, but this is yet to be found out, E theta dot, and we follow the same prescription. So, we take E theta cap vector at 2 time instants, it also rotates by delta theta as shown in this figure. Therefore, the difference vector is now, the magnitude is delta theta into 1, but please note the direction is along negative ER. This minus sign here comes because it is directed towards negative ER cap direction. So, negative ER cap, so that gives it this negative sign. Therefore, I have finally my time derivative of E theta cap as minus theta dot ER. So, remember why this minus came, because the change of E theta vector, the frame vector E theta changed in the direction of minus ER cap. Therefore, d ER cap d, and this we had derived earlier, d ER cap dt is theta dot E theta cap. Now, if you substitute these expressions in the acceleration expression that we have found, and combine these terms and collect terms of ER cap and E theta cap, you come to this expression of acceleration. I will remove this clutter here and write down the acceleration separately for you to see. Now, let us look at these terms. In the velocity vector, we have this radial velocity, which is along the radius, along the ER cap direction, and we have the tangential velocity, which is r theta dot, it is along E theta direction. So, it is tangential to the radial line. So, that way it is tangential. Whereas, in the acceleration, we have these 4 terms. The first term is the radial acceleration, we will call it as the radial acceleration r double dot. So, rate at which the radius is changing, this one. Centripetal acceleration, now that comes with a negative sign, which means it is towards negative ER. You see, if you open up the brackets, then the centripetal acceleration is towards negative ER, that means towards the pole, towards the center, it is centripetal. So, it is center seeking. So, it is towards the pole, it is negative of r theta dot square Er, and we have as the coefficient of E theta cap the tangential acceleration and the Coriolis acceleration. So, the tangential acceleration is perpendicular to the radial line, and as well as the Coriolis acceleration is also perpendicular radial line because it is along the E theta cap direction, but this has a different name, Coriolis acceleration. Now, let me remind you that the key step in all these derivations has been Er cap dot is theta dot E theta cap, and E theta dot is minus of theta dot Er, and this will come again later on. Let us look at a problem. The pin A, as shown in red in the figure, moves in a semicircular slot driven by a horizontal slot moving upward with a constant velocity v naught equal to 2 meter per second. Here you can see it is moving, this horizontal slot is moving at a constant velocity upwards. Calculate the normal and tangential components of the acceleration of the pin as it passes the position theta equal to 30 degree. You should note how theta has been defined. So, theta is increasing downwards, therefore, we have to be careful while choosing the coordinate system. Now, here I am using the plane polar coordinates for pin A. Er is chosen away from the center and E theta is chosen in the perpendicular to Er in the direction of increasing theta. So, the velocity of pin A can be represented by this expression. Now, note that since the pin A is moving on a circular slot, therefore, its radial velocity is 0. So, r dot is 0, therefore, we are left with only r theta dot E theta as velocity of the pin A. Similarly, in the acceleration expression, I have written out the acceleration complete acceleration expression first and then shown which components are 0. Now, r dot, r double dot, they are all 0 because the pin is moving on a circular slot, a semicircular slot. Therefore, we are left with these two expressions in the acceleration expression. Now, it is mentioned that this horizontal slot is moving up at a constant velocity of 2 meter per second. Now, what I have done here is I consider this vector b cap, which is vertically upwards shown by this black arrow. So, that is a unit vector direction, unit direction. I represent it as b cap. I represent b cap in Er E theta coordinates, in the polar coordinates that I am using. So, the representation of b cap, which you should be able to do, I mean you should be able to find out this representation of the unit vector vertically upwards as minus sine theta Er cap minus cosine theta E theta cap. So, this is the representation of this control direction, control motion direction, which is vertically upwards. So, representation of b cap in Er E theta coordinate system. Now, what is the condition given on pin A? So, pin A is moving because of this horizontal slot which is moving vertically up at a constant velocity. Therefore, whatever be the velocity of pin A, its dot with the unit direction b. So, its dot with b cap should be the velocity in the vertical direction, which is v naught, which is specified as 2 meter per second, and its constant velocity. Therefore, acceleration, whatever be the acceleration of the pin A, its dot with b cap once again should be 0, because it does not have any acceleration in the vertically upwards direction, in the direction of b cap. Now, if you use these expressions of V A, so here is the expression of V A and dot it with B, So, E theta cap gets dot product with E theta cap, with E r cap it is 0, dot product is 0 with E r cap. Therefore, I am left with minus r theta dot cosine theta on the left hand side. This leads to minus r theta dot cosine theta, and the right hand side is V naught, which is given to me. Therefore, theta dot, I can solve for theta dot, which was not known to me. I can solve now in terms of V naught r and the theta which is given, which is 30 degree. Similarly, for the acceleration, I take a dot product of the acceleration expression. This is our acceleration expression. I take a dot product of the acceleration expression with b cap, and this is what I have on the left hand side. Right hand side is 0, and from here, because I already know theta dot, which I found here, I can find out theta double dot. Now, once I have theta dot and theta double dot, I can complete my acceleration expression. So, I can complete my velocity expression and I can also complete my acceleration expression. So, theta dot and theta double dot are now solved. We can find out the complete velocity and acceleration expressions. So, that, and from there I can read out what is the radial acceleration, what is the tangential acceleration. So, I can read out this, I know theta dot, I can read out this because I know theta double dot, and this is what I have. So, this is a straightforward step, you should be able to verify this. Next, we move to coordinate systems in 3 dimensions. This is the Cartesian coordinate system, which is straightforward. Again, this I cap, j cap, k cap are unit vectors which are fixed with respect to distant stars. So, position vector is x I cap plus y j cap plus z k cap. I differentiate this to get my velocity, x dot, y dot, z dot. There is no derivative of the frame vectors because they are fixed with respect to distant stars. Okay, so they do not change direction, or they are they do not rotate, and they so the derivatives they vanish. And similarly, acceleration I can again differentiate once again the velocity expression to get acceleration expression. This is straightforward. Let us move to the cylindrical polar coordinates. Imagine a particle A moving in a certain way. Right now it is where I have drawn. I imagine a cylinder, a hypothetical cylinder with an axis as shown here by this dashed black line, and I choose arbitrarily a pole on this axis of the cylinder, and I join from the pole to A by this dashed line. Then I define a datum line which is perpendicular to my axis of the cylinder, arbitrary in an arbitrary direction, but it, as long as it must be perpendicular to the axis of the cylinder. So, datum line must be perpendicular to the axis of the cylinder. Then I drop down from A a line which is parallel to the axis of the cylinder, and wherever it meets on the plane of the datum line, of course rotated, so that distance is r. So, r is essentially the radius of this imaginary cylinder, and this theta is the measure of this radial line from the datum line. Remember, datum line is perpendicular to the axis of the cylinder. So, this radial line is also perpendicular to the axis of the cylinder. Therefore, our coordinates are this r, theta and z. Therefore, we have these unit vectors E r cap, E theta cap and E z cap. The directions are chosen like this, that E r cap is along the radial line away from the pole, E theta cap is in the direction of increasing theta, and E z cap is such that it is cross product of E r and E theta. So, E z is E r cross E theta. Okay. Then I represent the position vector of this particle A as r E r cap plus z E z cap, straightforward to see. So, the position vector is along this line. So, it is r E r plus z E z. Now, velocity is found by differentiating this expression of the position vector. This part is same as that we have discussed for the plane polar. This is an additional term now that comes in, and remember Ez is fixed in space. Ez is not changing its direction, only Er and E theta will change direction. Ez is the axis of the cylinder which is fixed. Ez is along the axis of the cylinder which is fixed. Therefore, Ez cap, the derivative of Ez cap is 0. Therefore, when I do a time derivative, this part is same as the plane polar coordinates, and this is z dot Ez cap. Straightforward. If I differentiate once again with respect to time, I get the acceleration. Once again you notice that this part is the acceleration in the plane polar coordinates, and this is the additional term because of Ez. So, this much for the cylindrical polar coordinates. Let us look at a problem in cylindrical polar coordinates. This problem says that a ladder of a fire truck rotates about the vertical axis with omega, this is shown here, of 10 degree per second, while the elevation angle of OA, so O is here, A is here. So, this elevation angle changes at a constant rate. So, this is the elevation angle, it changes at a constant rate of 7 degree per second, and OA extends at a rate of 0.5 meter per second. At the instant when theta is equal to 30 degree, theta is an angle which is shown here, and OA is 15 meter, determine the magnitudes of velocity and acceleration of the end A of the ladder. So, we have to find out velocity and acceleration of this point A. Okay. I will use the cylindrical polar coordinates. Here I have mentioned all the data that is provided in the problem. L is the length OA, I am expressing it by L. Now, the position of point A is L cos phi ER. Here I have shown the coordinate system, this is the coordinate system. So, L cos phi, which is the projection, this projection L cos phi ER plus L sin phi EZ. So, L sin phi is this length, so this times Ez, so that is the position vector. Now, velocity vector is obtained, I will differentiate this now. I will differentiate, I know the rules of differentiation, so I will differentiate that, and this is what we have. L changes, therefore L has a derivative, and cos phi, phi changes, so phi has a derivative, so minus phi dot sin phi ER. Then ER has a derivative, so L and ER dot is, remember ER dot is theta dot E theta. So, that is what I have used here. Then the second term you should differentiate L dot sin phi plus L phi dot cos phi times Ez. There is no derivative of Ez, Ez dot is 0. So, this is where we stop for the velocity, and once I have velocity I will plug in the values and I get this expression, and the magnitude of velocity is 2.96 meter per second, which you can check up. Now, the acceleration, I differentiate the velocity once again. Let us look at a few terms. So, I start differentiating L double dot cos phi dot. So, here I when I differentiate, so I get L double dot, but then L double dot is 0. You remember L dot is constant, so therefore L double dot is 0, so that does not figure in this expression. Then I will have L phi dot minus L phi dot cos sin phi. So, this is 1, and from another place I will have a derivative of L dot phi dot from here, L dot phi dot sin phi I will get again from here with a negative sign. So, this becomes minus 2 L dot phi dot sin phi. Similarly, I take derivative of second term with respect to phi dot etc. Then I have the frame derivatives, etc. When I do all these things and I assemble the whole thing, this is what I obtain. So, this is a after simplification I have obtained this expression. You should check this yourself, and finally, when you plug in the values, you get the acceleration vector in green as I have written out, and the acceleration magnitude is 0.672 meters per second square. So, that completes this problem, finding out acceleration, velocity and acceleration of the point A of the end of the ladder. So, to summarize, we have discussed the Cartesian, tangent normal and the polar coordinate systems both in 2D and 3D, and we have discussed some problems. So, with that I will close this lecture.